Remember in the last video we talked about the concavity, and basically the second derivative, when the second derivative is positive, it indicated that a function was concave up, and if a second derivative was negative, it indicated that a function was concave down. In the same way that if the first derivative was positive, it indicated that a function was increasing, and if the first derivative was negative, it indicated that a function was decreasing. So let's find the intervals where f of x equals x squared plus or times x, where that is concave up and concave down. So to check on concavity, we'll have to look at the second derivative. So let's start with the first derivative. We've calculated this a little bit ago. All right, and remember we have to use a product rule, so take the derivative of x squared, that's 2x, times e to the x, which is just the second, no derivative, plus x squared, no derivative on the x squared, times the derivative of e to the x, which is e to the x again. Okay, so we have that. All right, now before so we aren't quite done yet because we need to look at the second derivative. So let's do that. Now notice in the second derivative we have two terms. Each of them is a product, 2x times e to the x and x squared times e to the x. So we'll have to use a product rule on each of these terms. All right, well, we know we've already taken the derivative of x squared times e to the x, so let's just write that down. That was going to be this expression 2x e to the x plus x squared e to the x, and now we just have to take the derivative of this first term, and so I have to take using the product rule, take the derivative of 2x, that's 2, times e to the x, all right, plus 2x times the derivative of e to the x, which is e to the x. So I get this, and notice all of this, I can factor out an e to the x out of all of this, and I'll have an x squared, all right, plus a 2x and another 2x, 4x. And then plus 2. All right, now let's find out where these are each 0. All right, so if I do that, let's see, e to the x is never 0. To find out where this is 0, I have to use a quadratic formula. And so let's see, so the quadratic formula, I'll get the opposite of b, opposite of 4, plus or minus the square root of b squared, 4 squared, which is 16, minus 4 times 1 times 2, 4 times 1 times 2 is 8, so minus 8, all right, all over 2 times 1, which is 2, all right, and so let's see here, this is going to be negative 4 plus or minus the square root of 8, all over 2. Out of this 8, I can take a factor of 4. Since it's a perfect square, I can take its square root and bring it out of the radical, so I have negative 4 plus or minus 2 times the square root of 2 all over 2, and out of both terms in the numerator I can take a 2, and then I can take a 2 out of the denominator and cancel it, so I have negative 2 plus or minus the square root of 2. Now notice what that gives us. That gives us two factors here, and let me remind us how this works. Okay, so these are values that make this thing 0. So I should have a factor that's x minus one of these values, so x minus negative 2 minus the square root of 2, and another one x minus the other one x value, negative 2 plus the square root of 2. Right? And this is times e to the x. Now let's see, negative 2, well, when we subtract the square root of 2 is about 1.4, so this is about negative 3.6, and this would be negative 2 plus the square root of 2, about negative 0.4, I believe that would be. Okay, so let's just take a look at this. So then we'll have here a number line, and here at negative 2 minus the square root of 2, one place where the sign of this could change, and at negative 2 plus the square root of 2, have another place that the sign can change. And so let's see, so let's go out here. Let's say at x is equal to negative 4, all right, that would be to the left of about this negative 3.6. And if this is x is about negative 4, when I subtract this negative 3.6 from it, so it would be like negative 4 plus 3.6, I get a negative number. All right, when I take this negative 4 and I add, or I subtract a negative 0.4 approximately, or add a 0.4, I still get a negative number. And out here, of course, e to the x is always positive. So the whole thing is positive, and so out here we must be concave up. Let's check here at, say, at negative 1. Well, negative 1 plus 3.6, well, that would be positive. Negative 1 plus 0.4 roughly is negative, and e to the negative 1 is positive. So the whole thing is going to be negative. All right, so we're concave down. All right, out here, let's see, say at x is equal to 0. All right, well, we'd have 0 plus 3.6 roughly, that would be positive. 0 plus 0.4 roughly, so that would be positive. And of course, e to the 0 is one that's positive. So everybody's positive, so we should be concave up here. So take a look, we're concave up on the interval. I'll just put CU, concave up, on the interval from negative infinity to negative 2 minus the square root of 2, and from negative 2 plus the square root of 2, all right, to positive infinity, and we're concave down in between those, negative 2 minus the square root of 2 and negative 2 plus the square root of 2. Okay. All right, so let's take a look at this. Notice here we're at negative 2 minus the square root of 2. Before that, we're concave up. You can see it's slightly opening upward between negative 2 minus the square root of 2 and negative 2 plus the square root of 2. I'm sorry, Mathematica did this and it puts it in this order. We're concave down, and then finally past the square root of negative 2 plus the square root of 2, we're concave up again. Let's take a look at one more example before we leave this. We'll just wait. The next example we'll talk about an inflection point. Okay, so we'll stop here.